Hello, my name is Muhammad Umar. Welcome to ME 210 Engineering Dynamics. It is a subpart of engineering mechanics. Mechanics is the physical sciences that is concerned with the state of rest or motion of bodies subjected to the action of forces. Engineering mechanics is divided into two areas of study, namely statics and dynamics. Statics focused on bodies and equilibrium, such as at rest or move with constant velocity. Mathematically, it can be represented as Fr, which is the resultant force, equal to 0, which is the Newton's first law of motion. Engineering dynamics is the study of accelerated objects or motion. This subject is covered in two parts: kinematics, which considers the geometrical aspects of motion, such as displacement, velocity, acceleration, and time only. The second part is the kinetics, which is the analysis of the forces causing the motion. Such type of motion is studied through the Newton's second law of motion. Fr, the resultant force, is equal to ma. A is the acceleration of that object. To develop these principles, the course structure is divided into two parts. First, we shall discuss the dynamics of a particle, starting from kinematics and then kinetics with three different techniques, such as force and acceleration, the equation of motion, work and energy approach, and finally, the impulse and momentum approach. In most problems, we will be interested in bodies of finite size, such as rocket, projectiles, and vehicles. This will be followed by studying the rigid body's dynamics and two and then three dimensions. This tutorial's objective is to introduce the concepts of position, displacement, velocity, and acceleration. The most effective way of learning the principles of dynamics is perhaps to solve more and more problems. The book that I will follow is the Engineering Mechanics, Statics, and Dynamics by R.C. Hebler. If you don't have it, don't worry, I will share the downloading link below. Our roadmap is such that we will begin our study of dynamics by discussing the kinematics of a particle, that is a rectilinear or a straight line motion. Then we will study the curvilinear motion in three different coordinate systems, such as the Cartesian coordinate system, normal tangential coordinate system, and finally the polar coordinate system. Recall that a particle has a mass but negligible size and shape. Now let me introduce some basic terms that will be frequently used during the analysis of moving objects. Starting with position. Let's say a particle lies on a straight line at a distance s from a fixed reference point O. The length is measured in meters or in feet from the origin O. Mind that position is a vector quantity since it has both magnitude and direction. The displacement of a particle is defined as the change in its position. For example, if the particle moves from one point to another, the displacement is delta S equal to S prime minus S. The displacement of a particle is also a vector quantity, and it should be distinguished from the distance a particle travels. The velocity of a particle is the rate of change in displacement. If a particle moves through a displacement during the time interval The average velocity of the particles during this time interval between the initial and final position is V average equal to delta S by delta T. The instantaneous velocity is defined as V equal to limit of delta T approaching to 0 into delta S by delta T, or V equal to ds by dt. Since delta T is always positive, the sign used to define the sense of velocity is the same as that of displacement. Let me demonstrate the difference between average speed and average velocity. If a particle randomly moves from point A to point B following path 1 with a total distance of 30 meters in 6 seconds, and then follow path 2 of 12 meters in 6 seconds. So in this case, the average speed is 30 meters divided by 6 seconds, or 5 meters per second. And the average velocity is 12 meters divided by 6 seconds, or 2 meters per second. Acceleration is the change in velocity, either magnitude or direction per unit time. The average acceleration of particles during the time interval is A average equal to delta V by delta T. The instantaneous acceleration is a vector and defined as A equal to limit delta T approach to 0 into delta V by delta T, or A equal to dV simply by dt, or even it can be written as A equal to double derivative of the position vector of the displacement with respect to time. So here we go with the two important equations such as V equal to ds by dt and A equal to dV by dt. Now by eliminating dt, we arrive at another important differential relation involving the displacement, velocity and acceleration along the path, such as A ds equal to V dV. Although we have now produced 3 kinematic equations, but remember, the above equation is not independent, and only 2 unknown can be measured using these 3 equations. The position function of an object is the ultimate goal in solving kinematic problems. Position is related to other quantities such as velocity and acceleration. The knowledge of an object's position function can be used to find its velocity and acceleration function. Conversely, the knowledge of the velocity or acceleration of an object can help us to find its position function. Cool! The constant acceleration motion is a common phenomenon, and the above differential equation can easily be simplified into 3 kinematic equations. So let's do it. The first equation represents velocity is a function of time. How we get this? Well, by taking integration of the acceleration differential equation with the non-initial and final position of the 2 variables, velocity and time. This is the first and an important relationship between velocity and time. Our second kinematic equation provides position as a function of time from the velocity differential equation by taking the integration. Remember, we have to use the equation of velocity. It is a variable unlike acceleration. So the integration gives a relation between position and time. Here both are variables. If any one is known, the other can be measured through this relation. An important second kinematic equation, there should be no harm to memorize it. To get velocity as a function of time, take integration of the final equation. This is a relationship between the velocity and the displacement, since the acceleration is constant. Remember again that these equations are useful only when the acceleration is constant, and when t equal to 0 or s equal to s naught, v equal to v naught. A typical example of constant accelerated motion occurs when a body falls freely towards the earth. If air resistance is neglected and the distance of fall is short, then the downward acceleration of the body when it is close to the earth is constant and approximately 9.81 meter per square second or 32.2 feet per square second. Okay, so now let's try an example. This example from the book Hebler. It's chapter 12. During a test, a rocket travels upward at 75 meters per second, and when it is at 40 meters from the ground, its engine fails. Determine the maximum height, SB, reached by the rocket and its speed just before it hits the ground. While in motion, the rocket is subjected to a constant downward acceleration of 9.81 meter per square second due to gravity. Neglect the effect of air resistance. So we don't know SB and we don't know the final velocity before hitting the ground at c. So starting the solution, our positive direction is upward. And for the first part, let's consider point A where the rocket fails and the final position B, where the velocity reaches 0. Now, applying this third kinematic equation, which is VB square equal to VA square plus 2AC into SB, the final position, minus SA, the initial position. So VB is 0 and VA, the initial velocity given 75, taking whole square of it, plus 2 into acceleration. The acceleration is taken here is negative because the gravity direction is downward while our positive conventional sign is upward. Into SB, which we don't know, minus 40, which is the initial position. So we get the final displacement SB and it is 327. So for the second part, our initial position is point B and final position is point C. Applying the same equation between these 2 points gives VC square equal to VB square plus 2AC into SC minus SB. So we are looking for VC. We know VB is 0 at the maximum height, plus 2, again acceleration, and final in the initial displacement. So VC equal to minus 80.1 meter per second. Keep in mind, the rocket before striking the ground is moving downward direction. Therefore, it is negative. So here we conclude our example. Let's try one more example. In this example, the car is shown in this figure 12-2 in the textbook, moves in a straight line such that for a short time its velocity is defined by v equal to 3t squared plus 2t feet per second. Where t is in seconds, determine its position and acceleration when t equal to 3 seconds, when the initial time is 0 and initial displacement is 0 as well. So let's look at the solution. First, we find the position. We know that the function for velocity is given, and if you can recall, if we know the function of any of the variable velocity, position or acceleration, the rest of the variables can easily be found. So the differential equation for velocity is v equal to ds by dt. We know the initial position and initial time. So v equal to ds by dt, replacing v variable with the given function. Rearrange the equation, and now by taking integration, applying the limits for displacement from 0 to s and for time from 0 to t, which is known as 3 seconds. So after doing integration, we get s minus 0 equal to t3 plus t square minus the initial time. So our final equation for position is s equal to tq plus t square. And at t equal to 3 seconds, s equal to 3q plus 3 square. This gives us the total displacement car covers 36 feet. Now let's do the second part, such as finding acceleration. So once we know the function for velocity, we already know that the differential equation for acceleration. Replacing here v with the given function. And now taking simply the derivative of this function becomes a equal to 60 plus 2, and it's t equal to 3 seconds. Acceleration is equal to 20 feet per square second. And that is the answer.